Hey guys, welcome. So today we're going to talk about some applications of some linear ODEs. We're going to talk about an electric circuit model, and then we'll also talk about changing level of hormone model as well. All right. So the first application problem that I want to look at is the following electric circuit problem, where we're given basically we want to find what the current is, which we're going to call I here. Which of course will be in amperes, and the independent variable here will be, of course, be time, right? So we're going to assume that, excuse me, the circuit contains an an electromotive force, and that's going to represent our function E of t here, with an initial battery life of 48 volts. We have a resistor that is valued at 11 ohms, and an inductor that is valued at 0.1 henries. Right, and we're going to assume that the current is initially 0. Right, so rather than pretend that I have an extensive background in electric circuit modeling, we're going to just start out by saying that the model can be shown to be represented by this linear ODE here. And of course, once we divide through by L, we get the linear ODE here. And of course, if you don't like the way it looks now, just use the following change of variables. You can let X be T, you can let Y represent your I here. We're going to take our function P to be R over L, and we're going to take H to be R over L times T, right? And then if we do that, you get the following linear ODE, which is the Y prime plus P times Y equals E of T over L. And of course, this is a linear ODE because it can be written in the form that, we said we needed to be able to write it in for it to be linear. Now, if we go back and look at the original variables, we can say that our integrating factor here is going to be our E to the P of X with respect to X, or in this case, R over L with respect to T. And you can represent it either in your original variables as R over L over T, which I have here, or if you want to put in your specific values, we know that R is 11 ohms and that L is 0.1 henries, and you could calculate that your integrating factor is E to the 110 times T. All right, so now moving forward, we can derive that the exact solution is going to be E to the minus R over L times T, and then all of this junk is going to be what happens when we integrate our desired function, right? And then once, of course, we multiply through and simplify, of course, these two E terms will cancel out, which is good. And of course, these L's cancel. So we get E over R in the first term, and then we just get C times that exponential in the second term. Right, and that's our general solution here. So this is the general solution. Right, now of course we can take our R and L values that we defined earlier. R was 11, I believe you said L was 0.1, and we know that E started off, I believe, at 48 volts, so you can find your E of T to be 480. So plugging all of that into our general solution, we get that I has to be 480 over 11 plus C times E to the negative 110 times T. And then if we use the initial condition that I of 0 is equal to 0, you could eventually solve it, like, for example, this will just become 1. And then you're just going to, once you equate this equal to 0, move your 480 over 11 over, and you find that C is equal to negative 480 over 11, right? So nothing here is all that different from the previous examples that we did on linear ODEs. The only difference here is that somebody much smarter than me was able to come up with the original model here for the electrical circuit, right? Which of course is a linear ODE, which allows us to solve it. Okay. Now, the other application example that I want to look at is one that talks about the certain level of hormone in the blood of a patient that's varying with time. We're going to suppose that the time rate of change um, basically between a sinusoidal input of a 24-hour period from the thyroid and the removal rate, is proportional to the level present, right? So what we can eventually show, again, somebody much smarter than me would have come up with the model y prime plus k times y is equal to a plus b cosine of w times t, or most books will probably label this w as the Greek letter omega. So if I say omega, that's what I mean. So of course, here we see that we're in a linear form, and these constants k, a, and b, could be measured in the field of medicine, but we're just going to take them as arbitrary constants for now. Now, your integrating factor, of course, you're going to take your function that's in front of your y term here, and in this case, it's just the constant k. So you can get that your integrating factor, of course, is e to the k times t. Now, what does that mean for our solution? Well, that means that this is sort of the 1 over your integrating factor, right? So, of course, this is just, we can write it as e to the negative k times t. And then we have the integral of our integrating factor times our non-homogeneous term here. This is like your r of x, if you want to think of it that way. And then plus c times, again, 1 over the integrating factor. Now, if you do a little bit of algebra here, you can show, of course, once you integrate, the e to the kt term, you're just going to sort of get a k out front of that. Then you have to worry about this, the b cosine omega t term. You'll have to do that with, so I guess you would need like an integration by parts there, right? But the idea is that eventually with some work, you can show that this integral term will give you a over k plus b over k squared plus omega squared times this cosine and sine junk, right? So this would be sort of your general solution, right? And of course, to do anything, really significant with this, it would probably be helpful to know, of course, what A, B, and K are, right? And also omega as well. Now, one thing that you'll notice here is that this term here, this C times e to the minus kt, if we assume that our K is positive, and our t is positive, so that exponent is all negative, then you notice that as t goes towards infinity, this thing is going to decay to 0, right? So when t is extremely large, what you're going to be left with is just the other stuff, right? You're going to be left with this. And that's what's known as the steady state solution, right? So the reason why that's the steady state solution is because after a while, that's sort of what the system is going to settle into as far as a long-term or limiting behavior is going to be concerned, right? So I guess if you were to assume an initial condition, and for simplicity's sake, we'll just say y of 0 is 0 in this case, you could eventually show that C has to be this expression here, but again, for time's sake, I'm not going to go through it. But that is what you could get as far as your, and then of course plug that back into your general solution, and then there's your particular solution, right? So then the last thing is I've included a graph of what the particular solution would look like, and this could model the hormone level for some particular hormone in the bloodstream. All right, so those are 2 application problems on linear ODEs. So hope you enjoyed the video, and I will see you next time.